The VQ is a hybrid quantum classical algorithm designed to find the ground state of a quantum system. In this algorithm, a classical computer guides a quantum computer to produce trial ground states and to measure the errors. In this work, we will try to improve VQ, overcoming two problems. On one hand, measuring global entangled states requires deep circuits with multiple CNOT gates. This is problematic because we don't have perfect qubit coherence nor gate fidelity. On the other hand, evaluating the energy of the system requires the measurement of a large number of Pauli operators.
Two independent strategies can be proposed to overcome these difficulties. In first place, the idea of the circuit can be reduced by the means of the so-called hardware-efficient circuit, which restrict entangling gates to physically connected qubits. On the other hand, the number of measurements can be reduced estimating simultaneously multiple terms of the Hamiltonian by entangled measurements. In this project, we propose combining both ideas, implementing a VQA library for Qiskit that use hardware-efficient entanglement gates, or simply HEM.
Let's show how a grouping reduces the number of circuits of VQA. For instance, we can consider these three power strings. With local measurement, the respective values have to be computed separately, whereas with a chi-prime measurement, it can be done all at once. In order to take into account the hardware limitations, our grouping algorithm only assigns entangled measurements between physically connected qubits. As it can be seen in the table, we have significantly lowered the number of groups of several molecular Hamiltonians, without introducing too many CNOT gates.
We have obtained the Born energy of several molecules making use of improved VQA. As a proof of concept, we have successfully run an experiment using HEM for the lithium hydrogen molecule in the Guadalupe processor. We also ran classical simulation for the beryllium hydrate molecule. As it can be seen, HEM grouping converges faster than TPV, and is also less noisy than grouping with not hardware-efficient entangled measurements.
As we faced different obstacles, we thought of several ways to continue researching. First, the groups obtained depend on the order the Pauli strings are introduced as inputs. That is precisely what the histogram shows. Second, the order in which the qubits are mapped from processor to Hamiltonian matters, and we have some ideas to further improve the method using this fact. We will also seek for universal groupings. We want to extend these results to entangled measurements involving 3 qubits, and we aim to simulate bigger molecules. Finally, we would like to thank IBM for this opportunity and encourage anyone who might be interested to visit our GitHub repository.
Hello everyone. We are Corbinian, Joanna, Nicolo, and Friederike, that's me, and together we are the Quantum Anomaly Detection Team. If you are a physicist, have you ever stared at a complicated quantum many-body Hamiltonian and wondered how many distinct phases it has? Did you spend hours trying to compute different order parameters to find the phase boundaries? And did you get headaches from performing finite size scaling because the system sizes you can simulate with your classical computer are just way too small? Well, we did. But what if I tell you now that we came up with a way that lets you find all different phases of a Hamiltonian in a fully automated and unsupervised way without requiring any further information about your quantum system? And all of this is happening on a quantum device. NISQ-era devices currently have 2 promising applications: quantum simulation and quantum machine learning. We combine the best of both worlds and perform quantum machine learning with quantum data. And here's how it works. First, the ground states of the Hamiltonian that we want to study are prepared on the quantum device using the variational quantum eigensolver. Afterwards, we apply a second circuit which serves as the anomaly syndrome. At the output, a fixed subset of qubits is measured and a cost function is constructed from these measurement outcomes. The goal is now to train this quantum circuit to minimize the cost function on a small training set containing normal data points. Once a circuit is successfully trained, we can test it on normal and anomalous data, and hopefully the cost function will show a spike for data points that are different or anomalous.
To see if our quantum anomaly detector works, we tested it on the Bose-Hubbard model at half-filling. This model has a rich phase diagram, including a topologically non-trivial phase. We trained the anomaly detector on a single ground state, indicated here by the magenta points. You can see that the loss function is minimal in the part of the phase diagram it has been trained on, but considerably larger on the other 2 phases. So we were able to recover the tricky phase diagram by just looking at the anomaly syndrome. This here all happened on an ideal simulator rather than a quantum device, so next we test the quantum anomaly detection scheme under realistic conditions. For this we considered the Ising model, and we see that the scheme also works with the realistic noise profiles that we got from the real device. But wait, there's more. In the figure on the lower right, you see the order parameter in green. In blue, you see the noisy simulation, and in orange, you see the actual physical device. Wow, amazing. To get this to work on the actual device was rather tricky due to the large amount of noise, so we had to come up with some tricks. The three major improvements we achieved was through reducing the number of layers, taking into account the connectivity of the physical device for the entangling gates, and mitigating the measurement errors. Further details on this can be found in our report.
To summarize, we successfully implemented a quantum anomaly detector in Qiskit that can be trained in a fully unsupervised fashion using only a single training example. And it allows us to explore phase diagrams of quantum many-body systems on a quantum computer without requiring any previous knowledge about the system apart from the Hamiltonian. We would also be happy to incorporate our quantum anomaly detector into the Qiskit codebase such that other scientists can benefit from it as well. Thank you.
Hello everyone, I am Bartu Bishkin.
I am Jerzy Kotiarkowski.
I am Irfan Abedi.
I'm Martin Mauser.
I am Lana Rus.
And we're very excited to share with you our project, the Quantum Singular Value Transformation with Qiskit, or QSVT for short. QSVT is a relatively new framework for building quantum algorithms. It allows us to implement arbitrary functions, which are not necessarily unitaries. It also allows us to recast many known quantum algorithms in terms of the same simple circuit structure, serving as a unification scheme for these quantum algorithms. So, what is QSVT and how does it work?
QSVT is based on two main ideas. These are block encoding and quantum signal processing, or QSP. Block encoding is the procedure where you encode a matrix of interest, which is not necessarily unitary, inside the upper left corner of a bigger matrix, which is a unitary and therefore a valid quantum gate.
Quantum signal processing is a guideline for creating polynomial approximations to smooth functions by applying parameterized rotations iteratively. The parameters for rotations are the so-called QSP phase factors, and each function has its own unique factors.
QSVT then wraps up these two ideas neatly and tells us that one can perform this polynomial transformation upon this encoded block inside the unitary.
There are many QSVT implementable quantum algorithms, such as search, simulation, and factoring. In our project, we have chosen the simplest of these, the Grover's quantum search. We aim to bridge the gap between academia and the broader Qiskit community that exists around this topic of QSVT. And we think that quantum search is a very intuitive place to start. To perform a search, the matrix that we want to encode is actually 1 by 1. In other words, it's a scalar, which is the inner product of the initial and the target states. After encoding this inner product inside the unitary, we can then perform a transformation that would take this inner product from whatever value it has to the value of 1, making a complete overlap between the initial and the target states, resulting in the discovery of the marked state.
This working principle of QSVT search is fundamentally different from the original Grover's search in the sense that it is not flipping the sign of the marked element to perform amplification, but it directly transforms the inner product by using some kind of polynomial.
We are very happy to be a part of this amazing community, and we hope that our work here serves as a simple introduction to the groundbreaking ideas of quantum singular value transformation.